Okay, so today we'll study the sense of vision. We'll see how vision works in the humans. Okay. Here's a Benjamin Franklin quote: "An investment in knowledge pays the best interest." Okay, this is from your book. Okay. So vision is the most amazing and complex of our senses. Okay. It's the perception of light through the eye-brain system. So this device, it has to do is light when it falls on the retina, it has to convert that photon energy into an electrical signal. Okay? So that's what it has to do. So in understanding vision, there are three major disciplines. Physics describes light and how the image is formed on the retina. So if you're looking at an object, you want to form the image of that object in the retina. So here's an object. The first thing you have to do is to form an image on the retina. Okay? And that physics will tell you that, and physics tell you how that happens. And we saw that some of the principles involved, we saw that in the last chapter. Okay? Then physiology describes how this image is processed in the eye-brain system. So you have formed an image, and then the photons falling have to be converted into an electrical signal. The nerve impulses have to be sent to the brain. Okay, and so that part is physiology. And then you have perceptual psychology, deals with higher level processing. So you are getting all these electrical signals, nerve impulses, and then your brain has got to figure out that's a cat or a dog or whatever, okay, that you see. Okay. So it's quite complex. So this chapter concentrates on the physics of the image. So we'll talk about the physics of the image formation, and we'll talk some elementary physiology. Yeah. So like I said, the first step in the process of seeing is, if here's an object, you want to form an image on the retina. Okay? And you will see that in forming the image, two things do most of the refraction of the light: the cornea and the lens. Okay? Now, light rays from the object pass through many layers of material. They pass through the cornea, the aqueous humor, the lens, the vitreous humor, and finally form the image. The aqueous humor and the vitreous humor, they don't do much of the bending. The cornea does most of the heavy lifting. It does about 70% of the job. And the lens does the other 30% of the job. Okay? So in the image formation. Now here's another thing. The cornea and the lens can be treated as a single lens. Okay? So the cornea and the lens, if you look at your notes from the previous chapter, if you have two thin lenses that are close together, they can be treated as a single lens. Okay? If these are the two focal lengths of the lenses, they can be treated as a single lens, and the focal length of the single lens is given by this formula. Okay? So the cornea and the lens can be treated as a single lens. So the cornea and the lens can be treated as a single lens with strength equal to the sum of the individual strengths. Okay? So in this formula, by the way, the strength of a lens is 1 over the focal length. Okay? So the strength of the single lens is equal to the strength of the two lenses that are combined. Okay? All right, so in everything we we'll treat the cornea and the lens as a single lens. And the strength of that single lens will be the strength of the cornea plus the strength of the lens. Okay? Anyway, so the cornea and lens can be treated as a single lens with a strength equal to the sum of the individual strengths. So the cornea is where most of the refraction takes place. About 70% of the bending of light happens at the cornea. Okay. And the rest, 30% from the lens. Okay, 70 and 30% from the lens. Okay. So whenever you want, if there is a vision defect and you want to correct it, by surgery such as LASIK, what you do is you correct the cornea, you fix the cornea, because that's where you make small changes and you can correct vision. So hence, when vision corrective surgeries like LASIK are performed, changes are made to the cornea. Okay. The vitreous and aqueous humor have negligible contribution to refraction. These guys do not bend the light much. Okay. All right, so your eye, like we said, is amazing. Okay, so here's a far-off object, and the job is to form a sharp image on the retina. Here's a far-off object, here's a close object, and sharp images are formed on the cornea. Okay. So the cornea cannot change shape. Okay, so when you want to focus different objects, you have to change the focal length of this cornea lens combination. The cornea doesn't change shape, so the only thing you can do is change the shape of the lens to change the focal length of the combination. Okay. So when you're looking at close by objects, what happens is the lens gets thicker. When you're looking at far off objects, the lens gets thinner. When you're looking at close by objects, you have to bend the light more, and so you have to make the lens thicker. When you're looking at far off objects, the lens has to be thinner because you're not bending the light as much. All right, so how does this thickening and thinning of the lens happens? Okay, so again, when you're looking at different objects, the cornea is not changing shape. What is changing shape is the lens. Okay. All right. It turns out that the lens, okay, a ciliary muscle. So this is, now I'm drawing this looking from the front. Okay. This is a ciliary muscle. It is a sphincter muscle. A sphincter muscle is essentially a circular muscle. Okay. And the lens is suspended by little threads, you can say. So this is the lens. Okay, I'll draw the lens with a different color. That is the lens. All right, so when the ciliary muscles are relaxed, that circle is big, okay? And these cords pull the lens and make it thin. When the ciliary muscles contract, okay, this circle becomes smaller, the threads loosen, and the lens thickens, okay? So that's how, by contracting and relaxing the ciliary muscles, you can change the shape of the lens. And then you can focus different objects on the retina. Okay, so that's the physics of it. Okay, that's how the different objects are focused on the retina. Okay, so the cornea cannot change its shape while the lens can. When you're looking at the moon, that is a far-off object, the lens gets flatter, and that's because the ciliary muscles have relaxed, and this circle has become big. The cords pull on the lens, and the lens becomes thinner. Okay, so when you're looking at far-off objects, the ciliary muscles are relaxed. Ciliary muscles are relaxed. Lens is thinner. Okay, When you're looking at close by objects, ciliary muscles are contracted, lens is thick, and more bending is happening. All right. So when you're looking at nearby objects, your laptop, for instance, the lens gets more curved. Yep. So all this is controlled by the autonomous nervous system. So you can look at various objects, and this happens instantly, very fast. Okay. So your eye performs like a very high-end autofocus camera. Okay. So, you know, so your eye, so if your eye is normal, every object you look at is always sharply focused. There is no blur at any distance beyond 25 centimeters. So your eye is designed, 25 centimeters is about this far, less than, just a little less than a foot. From here to infinity, your eye is able to focus instantly almost. Okay? And how's that happening? By changing the thickness of the lens. Okay? By changing the strength of the lens. Even though the cornea is doing 75% of the focusing of the refraction, and the lens is doing 25%. Okay? It's the lens that can change its strength. Okay? And the cornea doesn't change its strength. Okay? So your near point is 25 centimeters. Like I said, just less than a foot. Okay? And you can focus from 25 centimeters to infinity almost instantly. Okay? So again, although the cornea performs the bulk of the refraction, the lens is needed for accommodation. So accommodation is, you know, how you're changing the strength of the lens to focus objects at various distances. Okay. With the crystalline lens, you'll not be able to, without the crystalline lens, you will not be able to change focus from distant object to nearby objects. All right, so there's the formula we'll use. This is the image distance. That is the object distance. And this is the focal length of the lens and cornea combined. Okay, so this is the lens formula that you saw in the last chapter. And you guys remember that the strength of a lens is defined as 1 over the focal length. Okay. All right, so again, we are treating the cornea and the lens as a single lens. Okay, so now let's do the numbers here. Okay, so the average size of your eyeball is 2 centimeters. Okay, so roughly this distance is roughly 2 centimeters, a little less than an inch. Okay, so the image distance is 2 centimeters. That's where the image is formed on the retina. Okay. So this distance is 2 centimeters, and we do all of that in meters. 2 centimeters, which is 0.02 meters. Okay, so 1 over 0.02 meters, okay. And 1 over d naught. D naught is the object distance. Okay, we'll come to that, and that is 1 over f. Is the strength of the lens. So that is the strength of this lens that you need. Okay, let's make sure we understand these numbers. All right, so let's say you want to see something, you want to see the moon. What is the distance to the moon? As far as you're concerned, that's infinity. Okay, so when you want to see the moon, d naught is infinity. Okay, so now I'm going to do the numbers here. So 1 over infinity plus 1 over 0.02. Multiply this by 100. 100 divided by 2, that is 50. This number is 50. Equal to the strength. Okay, this is 0 plus 50. Equal to the strength. So when you're looking at a far off object, the strength is 50 and if you look at your notes, 50 1/meter, that's diopters. Okay, so the units are 50 diopters. Yep. So the combination of these two, the cornea and the lens, which is acting like a single lens, the strength of this thing is 50 diopters when you're looking at the moon. All right, now let's say you are reading a book. You're reading a book, you're holding it at your near point. Your near point is 25 centimeters away. Okay? So now we'll read a book. And all this is worked out in a problem here on this page. Okay? But I'm walking you through it because I want to all right, so now we are reading a book. The object distance is 25 centimeters, equal to 0.25 meters. All right, so 1/0.25, and the image distance is still image distance is, whether you're reading a book or looking at the moon, the image distance is the same, which is 0.02 meters. And that is the strength you need. This is 4 plus 50. So the strength you need (4 plus 50) equal to 54 diopters. All right, so when you look at a close by object, you need a stronger lens because you have to bend the light more, and that's 54 diopters. When you're looking at far off objects at the moon, you don't need to bend the light as much, and so you need a weaker lens, which is 50 diopters. All right, so if you have a defect in the eye, so for instance, if I can't see far off objects, what that means is, so for the ciliary muscles cannot relax and the lens cannot get thin enough. Okay, so my accommodation might be from 52 diopters to 54 diopters. Okay, this would mean that, so this is my eyesight, 52 diopters to 54 diopters. I can read fine, I can't see far off objects. To see far off objects, what do I need? I need glasses, which are concave lenses with -2 diopters. Okay, so to see far off object, I use the assistance of these glasses. -2 plus 52 gives me 50 diopters that I need to see far off object. Okay, what if I can see far off objects and I can't read? Then my eyesight probably is 50 diopters to, my range might be 52 diopters. What do I do then? Then I use glasses with +2 diopters. +2 plus 52 gives me 54 diopters, and I can read close-up objects. Okay? All right, so if you can't see far off objects, what that means is your ciliary muscles cannot relax and make the lens thin enough. If you have trouble reading close by objects, that means your ciliary muscles cannot contract and make the lens thick enough. So that's what's happening. Okay? All right. Do you guys have any questions on that? We said a lot on that one slide. Okay. So, again, if you have normal vision, the strength of your the strength of your combined lens is changing from 50 diopters to 54 diopters. Okay, this is for distant vision. That's the power for distance. When you're looking at something that's very far away, this is when you're reading a book. Okay? When you're reading, you're looking at close by objects, you have to bend the light more to focus it on your retina, and so you need a stronger lens. Okay? And that is the combined strength of your lens and your cornea. And how are you changing the strength of your lens? It's by changing the thickness of the lens. Okay? How do you change the thickness of your lens? Your lens, okay, again, how do you change? So here are your ciliary muscles. The lens is suspended. So this is the lens. The lens is suspended from the ciliary muscles. When the ciliary muscles relax, the lens gets thinner. When the ciliary muscles contract, the lens gets thicker. Okay? So when you want to read, your ciliary muscles are contracted, your lens are thicker, so you're straining your eye. And when you're looking at far off objects, that's when the ciliary muscles are relaxed and you're not straining your eye. Okay? So if your ciliary muscles are not able to do their jobs properly, that's when you have defects. Okay, eye defect. You can have eye defects also if your eyeballs are not are out of whack, if they're too long or too short. Okay? So that can cause problems as well. All right. So when viewing a close object, the eye must be more converging to cause the rays to move retina. So when you're looking at close objects, you have to bend the light more to focus the object on the retina. Okay? A sphincter muscle action in the eye adjusts the thickness and strength of the lens, doing the fine-tuning necessary to produce the image precisely. And the sphincter muscle is relaxed and the lens is thin when you're looking at far-off objects. Okay, so the sphincter muscle is relaxed. So okay, let me. Okay, I will do two diagrams. So this is highly exaggerated. This is looking at front view. Oops. Okay, so when the sphincter muscle is relaxed, these fibers pull on the lens, make the lens thin, and you're looking at far-off objects. When the sphincter muscle is contracted, the lens gets thicker, and you're looking at close-by objects. Okay, so that's how you change the focus of your camera. Okay. All right, so the sphincter muscle is relaxed and the lens is thin when looking at far-off objects. The muscle is tensed and the lens thick when focusing on nearby objects. Okay. So now we'll go over the numbers. Okay. So the strength of your lens changes from 50 diopters to 54 diopters. Again, you need a strong lens to read close by objects. You need a weaker lens when you're looking at far off objects. Okay. So the average adult lens to retina distance is 2 centimeters. Okay, so the image distance is 2 centimeters. Okay, so again, this is the formula. that we go to 1 over the focal length, which is the strength. This distance is 2 centimeters, so 1 over 0.02, that's 50, and that's the 50 diopter. Okay. For the human eye, the image distance is 0.02 meters. 1 over 0.2 is 50. Okay. The normal range of clear vision is 25 centimeters for reading to far point of infinity. When you're looking at far points, this is infinity, that becomes 0. So the strength needed is 50 diopters. Okay. So when you're looking at far off object, DO is infinity. This is 0, 1 over 50. Okay. And so the strength is 50 diopters. So when you're reading, so DO is, the object distance is 0.25 meters when you're reading, and DO is infinity when you're looking at far off objects, when you're looking at the stars. Okay, so the strength of the normal eye varies between 50 diopters to 54 diopters. So that's the range of your strength. Okay, so here in this problem, it's all worked out. Okay, so the strength is 1 over F is the strength. This is the strength. Okay, so DI is 0.02 meters, and when DO is infinity, when you're looking at far off object, the strength is 50 diopters. When you're reading, DO is 25 centimeters, so which is 0.25 meters, and the strength is 54 diopters. Okay. You're looking at stars. Okay. All right. So the maximum strength is 54 diopters, which is only about 8% greater than the 50 diopters. So the strength of your lens cornea combination can change by about 8%. That's the accommodation you can do. And how do you do that again? By relaxing and contracting the ciliary muscles, which thins and thickens the lenses. Okay, so that's how you do it. And if you have eye defects, where does that arise from? There are ciliary muscles not able to completely relax or contract. If you're not able to completely contract, then you have trouble seeing close by objects. If you're not able to completely relax, then you're having trouble looking at far off objects. Okay? Accommodation ability is usually better than 8% when the person is younger than 40 years. Okay? But it decreases steadily with age. Okay? So you start having problems after 40 years, generally. All right, now we'll talk about visual acuity. Okay. What this means is the following. So let's say you're looking at the headlights of a car. If the car is very far away, this will appear as one light. And I don't know if you've experienced this, but if the car is too far away, it might appear as a motorcycle. Okay? So how detailed is your vision is what we're looking at. So the human eye can resolve points with a minimum angular separation of 3 times 10 to the minus 4 radians. It can see these as two separate objects if this angle is 3 times 10 to the minus 4 radians. That is 1 minute of an arc. That is 1/60th of a degree. Okay. What that means is humans can resolve details as small as the diameter of a human hair held at arm's length. So at arm's length, if these 2 points are separated by the width of a human hair, you can tell there are 2 points. Okay, that's what that means. Okay. Here's another way to say it. Okay. A car's headlight will appear as 2 spots from as far as 4 kilometers or 2.5 miles. So if a car is 3 miles away, your eye is not able to separate the 2 lights. It'll appear as 1 light. Okay? So if the car is 2 miles away, then you'll see 2 headlights. Okay? So that's what that means. Okay, here's how this works. Okay, so again, remember when you see something, what you have is you have formed an image on the retina, and the retina has cells, rods and cones. It's the cones that we'll be talking about. Okay, so rods and cones, and the image is formed on the rods and cones. Okay, so here there are 2 dots formed on the rods and on the retina. Okay, if those 2 dots are formed on these 2 cells separated by a cell, then they will appear as 2 dots. If these 2 dots are formed on the adjacent cells, they'll appear as 1 dot. Okay? So for you to distinguish that there are 2 dots, their image has to be formed on 2 cells with at least 1 cell. There's with a gap of at least 1 cell. Okay? And that's when you can tell if there are 2 dots. Okay, when will this happen? So if you want to increase your visual acuity, what you'll need to do? If you have more cells, then your visual acuity will increase. Okay? So it turns out that in the human eye, there's a spot on the retina called the fovea, which has a high density of cells, of cone cells. And your sharpest vision is when the image forms there. Okay? So your eye is designed so that when you're looking at straight out objects, that image is formed on the fovea, and that's when your vision is the sharpest. If you're looking at an object on the side, you don't focus it as sharp. Okay, you don't see as much detail. Okay, so straight head on is what you see is you see the sharpest. Okay. All right, so the higher the density, sharper your vision. Okay, you can tell 2 dots separately. Okay, again, to be able to tell 2 dots are separate, the image of 1 dot needs to be here, and there needs to be a cell where the light is not falling, and notice the image of the other dot needs to be on that cell. Okay, so for the eye to resolve 2 dots, their image must fall on 2 non-adjacent cells on the retina as shown. If the images of the 2 dots fall on adjacent cell, if this were over here, then they are interpreted as a single larger dot by the brain. Okay? So if the second dot fell over here, these 2 dots, the brain will think that you're seeing 1 dot. Okay? So going back to that example of the car, if the car is more than 3 miles away, 1 headlight image is formed here, the other headlight image is formed here, and what you'll see is a motorcycle and not a car. Okay? So the fact that cell B gets less light than its neighbors tells the eye-brain system that there are 2 images instead of a single image. Okay. All right. So there's the fovea. Okay. That has high density of images. Okay. The fovea is a small pit in the retina that's responsible for the highest visual acuity. Okay. So there it is. When the image is formed there, that's when you see the most details. If the image is formed here, so if I'm looking at something low there, side view, that image is formed over there, and that image won't be as sharp. I can look at that guy, that image is formed on the top left, and that won't be as sharp. The sharpest image is when I look at this object straight on. Okay? All right, so here are some of the numbers. Okay, if someone has 20/20 vision, here's what these numbers mean. The first number refers to you, and this refers to the general population. Okay, so if you have 20/20 vision, they can see clearly at 20 feet what normally can be seen at this distance. So this is the average vision. Okay, so if an average person with good vision can see something at 20 feet clearly, and you can also see at 20 feet, then you have 20/20 vision. If you have 20/40 vision, see this number is less than 1, that means you have worse vision. Some person who can see at 40 feet, 40 feet is roughly, it's roughly half the width of this room. Okay, if a normal person can see clearly at 40 feet, you have to be at 20 feet to see it clearly. Okay, so your vision is worse. If you have 20/15 vision, a normal person with good vision can see this stuff from 15 feet. You can see that from 20 feet. Okay, so your vision is better. All right, so that's what those numbers mean. All right, so now we'll compare our eyesight to an eagle's eyesight. Okay? Eagles are generally considered to have the best eyesight in the animal kingdom. Eagle's eyes are roughly the same size as the human eye, so the eagle eye is roughly the same size as the human eye. Eagles can see an object as small as a rabbit from 2 miles away. Okay, so 2 miles is so an eagle can see a rabbit from here to the racetrack. Okay. Visual acuity, eagles have 25 vision. Okay, what that means is, see, their acuity is almost 4 times greater than ours. Okay, 5 times greater. Okay, they can see what we can see from 5 feet. They can see from 20 feet of it. That's what that means. Okay, meaning they can see at 20 feet what a human with good vision can see from 5 feet. Okay, so what I can see from here, that bottle, the eagle can see clearly from 20 feet. How do you make your vision sharper? We already said this. You guys remember? Okay, when the density of cells on the retina is higher. When you have cells closer by, remember that's when you make your vision sharper. Okay, so what we're saying is the following. So if the density is higher, remember these 2 dots will appear as separate dots. Okay, and with the higher density, this vision is sharper than this vision. Okay. All right, so that's what's happening in an eagle's central fovea has 1 million cones per square millimeter. A square millimeter is that much. An eagle has 1 million cones per square millimeter, while the human fovea has 200,000. So it has 5 times the density of cells. And so its vision is almost 5 times better. Okay? And that's why it can see a rabbit from 2 miles away. Okay. So predatory birds like eagles have multiple foveae. They also have multiple foveae. We have only one fovea. What is a fovea again? It's it's a small area of high density cells, okay? So this, if an image is formed over there, that's where you see the sharpest, okay? And so we have evolved to be able to see stuff directly in front of us sharply, okay? There are multiple foveae allowing for both sharp forward vision and excellent peripheral vision, while humans have only one central fovea. Okay. Eagles have 340-degree field of vision, so an eagle can see 340 degrees, and humans can roughly see 180 degrees. It's actually maybe about 200 degrees. Okay. And we'll come to this shaded region in a second. Okay. That's associated with binocular vision. All right, we have two eyes. And why do we have two eyes? For depth perception, okay? So now your brain is able to adapt even if, let's say, you were born with one eye. Here's what you would do. You would move your head, and if an object moves, that's how you could get depth perception. But if everything was still and you didn't move, you need two eyes for depth perception, okay? In binocular vision, an animal has two eyes capable of facing in the same direction to perceive single three-dimensional images of its surroundings. So you need depth perception to see three-dimensional images, okay? Having two eyes rather than just one eye gives a wider field of view. Okay, so you see this portion, your right eye can see, the left eye cannot see this portion. And here is a portion that the left eye can see that the right eye cannot see. Essentially, each eye is seeing 180 degrees. Okay? All right. So, for example, humans have a maximum horizontal field of view of approximately 200 degrees. Okay? And if you move your eye a little, that can be increased to 220 degrees. About 120 degrees of which makes up the binocular field. 120 degrees, both eyes can see this field. Okay. All right. So here's how you get depth perception. Okay. So if you're looking at far off objects, okay, your eyeballs are not as turned inward. When you're looking at a close by object, your eyeballs have to be turned inward. And your muscles, there are muscles in your eye socket that do that, and that gets fed back to the brain. So the harder the muscles are working, the closer the object is, and that's how you tell an object is close by. So when two eyes focus on the same object, they will angle inward toward each other. That's called convergence. Depending on the distance of the object, the eye will converge more for close-up objects or less for distant objects. So the convergence is more for close-by objects than for distant objects. The extra effort used by the muscles on the outside of each eyeball gives a clue to the brain how far away the object is. Okay? So from the effort needed for convergence, that's how you get depth perception. Okay? Two eyes give stereopsis, in which binocular disparity by the two eyes' different position on the head gives precise depth perception. Okay, so if I'm looking at that glass, my left eye is getting this perspective, my right eye is getting this different perspective. Okay, so it's parallax. So for instance, if you want to see this, you can, if you want to see this effect, what you can do is open one eye, hold your thumb against that glass, and that glass is hiding behind the thumb right now. And when I open the other eye, I can see the glass. Yes. Okay. So your eyes are getting different perspectives. Anyway, so you need two frontal eyes for depth perception. If you had two eyes on the side like that, like fish, you wouldn't get depth perception. Okay. You need to be able to see the same scene with the two eyes. All right, now we'll talk about vision correction. Okay. Again, normal, if you have normal vision, the strength of your eye can change between 50 and to 54 diopters. 54 diopters when you're reading close by object at 25 centimeters, and 50 diopters when you're looking at a far off object, like the stars. And so if you have problems, that means your range is not between 50 and 54. It's, let's say, 52 to 53. So this is a problem. So 50 to 52, that means you can see distant objects, but you can't read close by objects. Okay. This is problem 1. So this is your far-sighted. You can see. Problem 2. So 52 to 54. You're nearsighted. You can read nearby objects fine, but you can't see far off objects. Okay. The most common vision defects are myopia, nearsightedness. This is nearsightedness. And hyperopia, farsightedness. You can see far off objects, but you can't read close by objects. Okay. So how do you fix that? You give to fix this, you give a convex lens of strength plus 2 diopters. To fix this, you give a concave lens of strength minus 2 diopters. This plus this gives you 50 diopters to see far off objects. This plus this gives you 54 diopters to read close by objects. Okay. So that's how you fix those things. Okay, so the most common vision defects are myopia, nearsightedness, and farsightedness. Okay, so in nearsightedness, when you have a close by object, so no, in nearsightedness you can't see the far off object, and so when you can't see the far off object, your lens and your ciliary muscle is not able to relax completely. Okay, it's still half relaxed, so the lens is too thick, and the image is formed in front of the retina. The light is being bent too much. So what you do is you give a diverging lens. You diverge the incoming rays, and so you can form an image finally on the retina. Okay. All right, so if you're nearsighted, you can't see far off objects. And when can you not see far off objects? When your ciliary muscles cannot relax and the lens cannot become thin enough. Okay. All right, so in diopters, this is the numbers. Okay, so when you have farsightedness, you can see far off objects. You cannot read close by objects. To read close by objects, your ciliary muscles have to contract, make the lens thicker, and if your ciliary muscles are not able to contract enough, then you can't read close by objects. Okay, so that's farsightedness. So the cause for both defects can be either a lens of incorrect strength or an eye of incorrect length. Okay, so I described the lens of incorrect strength. It could be that your eyeballs are of incorrect length. Small imperfections such as an eye that is 0.01 centimeters too long. So an eye that is 0.01 centimeters. 0.01 centimeters is a tenth of a millimeter. You guys know a millimeter is that much. A tenth of a millimeter. If your eye is out of whack by a tenth of a millimeter, then you would have problem. Or a lens that is 0.5 diopter too strong causes noticeable deficiencies. Okay. So I mean, if, I don't know if you've worn glasses whose strength are plus minus 0.5 diopters and so on. Okay. So nearsightedness, you can see objects close by, but you can't see far off objects. What that would mean is, so your ciliary muscles cannot relax enough to make the lens thin enough to see far off objects. Okay, so your strength is not coming down to 50 diopters. The strength of this lens is greater than 50 diopters, okay, as shown. So it's too thick and it's here's a far off object. The ciliary muscle is not completely relaxing. The lens is too thick and the image is focused in front. And so if you give a diverging lens, this will diverge the incoming rays and that image will be focused on the retina. Okay. And this has a negative strength, and that's how you fix that. You give a negative strength. This plus that gives you 50, and you can see far off objects. Okay. The myopic eye cannot relax its lens enough, relax its ciliary muscles enough to make the lens thick, okay, enough to avoid over convergence. To correct a myopic eye, a diverging lens of negative strength is used. So a diverging lens of negative strength is used to give you, so you can see far off objects. Okay. Far-sighted people can see far off objects, but they cannot read. Okay? They can't read close enough object. So their ciliary muscles are able to relax and become thin to see far off objects, but they're not able to contract enough to make the lens thick enough to see nearby objects. Okay. So the problem is, so your lens cannot become thick enough to give you a strength of 54 diopters. Okay. So far-sighted people have 50 diopters to, let's say, 52 diopters. Okay. What you need is 54 diopters. So to fix that, you give them a converging lens of plus 2 diopters. This plus this will give you 54 diopters. Okay. So a far-sighted person can see distant objects clearly, but close objects are blurry. Okay. So you can see clearly the far-off objects, but a close-by object, your lens cannot get thick enough, and so the image is formed behind your retina. Okay. You need to aid this lens, and you give a positive power glasses to convert these rays more to form an image over the retina. Okay. Yeah. The lens of the hyperopic eye has insufficient strength to converge lens from a close object to the retina. So a close object, so your ciliary muscles are not contracting enough to make this thick enough to focus it on the retina. Okay. For an eye of normal length, this means that the maximum strength of the eye is less than the needed 54 diopter. It's less than 54 diopter required for reading. To correct for a hyperopium, a converging spectacle, okay, of positive strength is used. Okay. So a converging lens is used. Okay, this problem goes through that. So a myopic person can see objects clearly from no further away than 1 meter and has a lens to retina distance. Okay. So the strength is, so here's the image distance and here's their far point, and their strength goes from 50 diopters to 51 diopters. Okay. Oh, so, oh no, they're, so 51 diopters, so their strength is from 51 to 54 diopters. Okay, so they're given a corrective lens of -1 diopter to make that 50 diopters to be able to see far off objects. Okay? So here's how you can test astigmatism. Okay, so astigmatism is, so if your lenses are perfectly, if your cornea and lenses are perfectly spherical, this will be focused properly, this will be focused properly, and all these lines will be focused properly. So you can detect astigmatism. For detecting astigmatism, if some of the lines appear darker or clearer to you than others when viewed without corrective lenses, you have astigmatism. Check each eye separately and look at the center of the image. So what you want to do is remove your glasses. If you're wearing glasses, cover one eye and look at these lines. Look at the center. And if they all appear equally dark, then you don't have astigmatism. Okay? So you'd have to do that for a close by. Can you see the difference? Can you see the difference from there? You have to do it close by, like that. So with my right eye, anyway, I have astigmatism. Yeah, so you can check it out. So here's the problem. See, with astigmatism, see, the image is focused like that. Some of the part of the image is on the retina, other parts are not. That's because of the misshapen cornea. Okay? And so that can be corrected as well. So astigmatism often can be corrected by using spectacle lenses with opposite asymmetry of the astigmatic eye. Okay, so if the eye is curved more one way than the other, the cornea is curved more one way or the other, you correct it by using spectacle lenses that have opposite symmetry of the astigmatic eye. Okay? If the astigmatic lens is too strong vertically and too weak horizontally, a lens that is diverging vertically and converging horizontally can correct the problem. Okay? All right, now we'll briefly talk about color vision. Okay, so on your retina, you have two types of cells, rods and cones. Rods they function in low light and they don't have color vision, so they're black and white. And you have three types of cone cells. These guys are more sensitive to blue light, red light, and green light. Okay? So on the fovea, where the highest density of cells are, which gives you the greatest visual acuity, only cones are present. Rods are not present. Okay? So the sharpest vision is also color vision. Okay? These guys work in bright light. These guys work in dim light. So in dim light, you cannot see color. Okay, so if the light is too dim when only cones are working. Okay. Rods and cones are photoreceptors. What does that mean, photoreceptors? They can absorb a photon and generate a nerve impulse. Okay, so they're photoreceptors in the eye that convert the energy contained in a light photon to electrical signal that can be sent to the brain via the optic nerve. Okay. There are 130 million rods found throughout the retina, except for a small region in the center of the fovea. Okay, so in the fovea, there are no rods. Rods are more sensitive than cones. Rods are can be about 1,000 times more sensitive than cones. Okay? And are solely responsible for vision in the dark. in dark environment and peripheral vision. Rods do not yield color information. Okay, so they provide black and white information. So the rods are good for low light and low light information, seeing in low light. Cone vision is associated with 7 million cones. So humans have 7 million cones, 130 million rods. Okay, and are concentrated in the fovea. Okay, so in the central part. So cones are concentrated there. Okay. There are 3 types of cones. So there are 3 types of cones. And this one is sensitive to these wavelengths, blue wavelengths. This cell, it's called a green cone because it's sensitive to those wavelengths. And the yellow cone, which is sensitive to those wavelengths. Okay. Shown is the absorption characteristics of the 3 cone pigments in humans. About 8% of men and 1% of women are partially colorblind. Partially colorblind meaning they probably don't have one of the 3 different kinds of cones. Okay. Most of them are missing only one type of cone, and the various type of color blindness corresponds to the absence of different types of cones. So if you're missing that, that's one type of color blindness. If you're missing that, that's another type of color blindness and all. Okay. There are also rare individuals who lack all 3 types of cones and are totally colorblind. Yes. So if you lack all 3 types of cones, then you're totally colorblind. Rod cells are photoreceptor cells in the retina that help with vision in low light. So rods help with vision in low lights. Rod cells convert photons into electrical signals that the central nervous system processes. They're responsible for black and white vision in low light. Okay, so with rods you only get black and white vision. Rods are concentrated in the outer retina, so they're good for peripheral vision. Okay. With their density increases towards the periphery. So their density increases towards the periphery, so you get good peripheral vision. There are no rods in the central fovea. Okay. Rods are about 1,000 times more sensitive to light than cones. They're most sensitive to blue-green light with a peak sensitivity of 500 nanometers. Okay. Rods have slow response speed, low spatial acuity. What does low spatial acuity mean? Their density is low. Remember, if you want high acuity, if the cells are densely packed, then you have high acuity. The vision is sharp. So rods are not densely packed, and so you don't see much detail. Okay, so the image is not sharp. Low spatial acuity and low contrast sensitivity. They cannot function during the day because they're photo-bleached, so they're saturated during the day, so rods don't work during the day. Okay. Rods evolved about 500 million years ago to help organisms survive in low light. Okay. So, so here is how color vision works. Okay. A simplified theory of, oh, wait a second, so let's see. Okay. So here is a color vision. Humans can see light in the range of, 380 to 750 nanometers, 380 to 750 nanometers. The 3 types of the cells in the retina to red, green, and blue light allow the perception of colors through color blending. The average human can see around 1 million different colors. Okay. This is because the human eye has 3 types of cone, each of which can register about 100 different color shades. So the idea is the following. So each cell has, you can think of that as 100 different values of color settings, okay? And you have 3 of those, so 100 times 100 times 100, that is 1,000,000, okay? And you can see 1,000,000 shades, okay? So you can think of this like this, okay? When this cell is excited, its excitation level can be anywhere from 1 to 100. So this is a simplified picture. So let's say the blue cell is excited to a level 5, the green cell is excited to a level of 13, and the red cell is excited to a level of 55. This will appear as one color to your brain. Okay? So this can take 100 values, 100 values, 100 values, 100 times 100 times 100. You can see 1,000,000 shades. Okay. There are some people who have a 4th type of color cell, a cone. These people can see 100 times 100 times 100 times 100, 100 million shades. Okay. Some people have 4 types of cones, an additional orange one. This allows them to see 100 million shades. Okay. That's 1 in 100%. Okay. The human eyes can perceive more variation in warmer colors than cooler ones, because almost 2/3 of the cones process the longer wavelengths, red, orange, and yellows. Okay, so there are fewer cones in the blue side that process the blue colors. Okay, color blindness can occur when one or more of the cones are not functioning as expected. So here's how you see colored objects. So when something appears blue, so white light contains all the colors and blue is reflected. All the other colors are absorbed. So that chair appears blue because white light falling on it, all the others are absorbed, but blue is reflected. When something appears red, the red is the red is reflected and the rest are absorbed. Here's an interesting one. You can take a white sheet of paper and shine red light on it, and it'll appear red. Because a white sheet of paper reflects all colors, and now it's reflecting, if you're shining red light, it's reflecting red on it, and so it appears red. A dark object absorbs all of them and appears dark. A gray object absorbs everything partially, and so it appears gray. White objects reflect all wavelengths equally well, and a black object absorbs all wavelengths equally well. Gray is a partial absorption of all wavelengths. So true color is perhaps more accurately defined as reflecting characteristics of a substance. So when a certain object appears a certain color, it's reflective characteristics. Okay. All right, guys, so that finishes